Okay, so today I'd like to talk about a couple of things. It's an important topic, rigid body modes. Modes, specifically for the beam column element that we started last time. Okay, this becomes a bit more involved than what you saw in the case of trusses, right? And then once we talk about the rigid body modes, and again, we're going to see an introduction of some form of a RBM matrix. Okay. And once we talk about that, we'll pull it together, and this will allow us to define the element stiffness matrix. Okay, and so this is sort of should conclude the theory portion of the beam column elements, and then we'll do a couple of examples. Okay, but let's get into the rigid body modes. So last lecture we covered the basic system, right? Among others. Okay, and here on the basic system, if you look at at your element, okay, kind of fix it like this, right? What you see, right, is the element builds two moments, okay, that we called F over bar prime 1, right, and F over bar prime 2 like this, okay? Counterclockwise is a positive direction, right? And then we pick up an axial force, which we denoted by F over bar prime 3, right? So the two moments and a force, okay? And so under that action of forces, right, put this guy on the roller, right, you can displace by a certain amount, right, under the action of F prime 3. That displacement was given by delta over bar prime 3, right? And then you can develop slopes, right, or rotations, same thing. Okay, this guy was called everything counterclockwise possible. This slope or this rotation, right, because we're talking about small angles, it's the same thing. Delta prime 1, okay, and this guy can develop a rotation, right, counterclockwise, positive, delta over bar prime 2, okay. This is what happens in the basic system. Now, let's go to the local system. Okay. And in the local system, right, we have an element, right, and that element can develop the following displacements, right? Delta prime 1, right? Delta prime 2, okay? Let's skip the rotation for a second. Delta prime 4, delta prime 5, okay? So then under the action of these displacements, okay, let's say this node moves to the right and up. This node moves here, okay, and this node moves there, okay, under the action of these displacements. So this now is your new element, okay. Let's denote it with a dashed line like this, okay. So this is our little x. Okay? At the same time, let's draw a line here that lines up with a little x-axis too. Okay. Right. So now okay? I also want to denote by delta prime 3, right? And delta prime 6, right? The corresponding rotations. Okay? And what makes sense to do, right, especially when enforcing boundary conditions and so forth, right, is to define the rotation, okay, with respect in the system, right, to the little x coordinates, okay? So then imagine this, right? The element is displaced under the action of delta 1, delta 2, delta 5, and delta 4, right? And then it undergoes some rotation, okay, locally. Okay. And that rotation will be exactly delta over bar prime 1, okay? So you can see that this is a rotation with respect to the configuration that's been displaced, okay? However, when I talk about delta prime 3, I want the total guy, okay? So then this guy, I will denote by delta over bar prime, sorry, no over bar here, delta prime 3 like this, okay? Again, this is done in the interest of being able to set up, boundary conditions, right? So for example, if you know that at a given location, your delta prime 3 is something, okay? It's hard to set this guy first, right? Because you don't know how much your element's going to displace, right? However, if you make the delta prime 3 relative to the unsort of rotated configuration, right, before the element displaced, then you can set boundary conditions. So I think this is the cleverness here, right? And then the same thing happens with the delta 6, right? So supposedly, right, you rotate by this much, okay? Right, you draw the axis that's parallel to x. This big guy becomes delta prime 6, right? And this little guy that will generate moments, okay? So the key is that the overbars, right, delta 1 and 2, will generate the moments. And the part of the rotation that generates a moment, right, is the part that's relative to the displaced configuration. And everything else is eaten up by the rigid body motions, okay? And so in that case, right, what remains to be done, right, is to relate delta over bar, right, prime, and delta prime as vectors. Okay. All right. So let's do that. Okay. So let's look at the rotation in the basic coordinate system. All right. Delta prime 1. Okay. What does it equal to? Right. It equals to delta prime 3, right? The larger, possibly larger rotation. 3, right? And from delta prime 3, I need to subtract this angle here, okay? So what is that angle, right? The angle for small angles is the same as the sine of the angle, right? And the sine of the angle is vertical distance, right? This vertical distance here, divided by the length, okay? So the vertical distance here is exactly delta prime 5. Okay. Right. Okay. The vertical distance here is exactly delta prime 2. Okay. And then the difference becomes, right, you get minus vertical displacement of node J, delta prime 5, minus delta prime 2, which is a vertical displacement of node I, okay? This gives us this vertical distance here, okay? And then this vertical distance gets divided by the length of the bar over delta L, over L, okay? And so as you can see, right, we're taking the total rotation, right, or total angle, total rotation, right? And from the total rotation, we subtract, okay? Rotation due to rigid body modes. Okay. Right, so the same analysis holds for delta over bar prime 2, right? We start with delta prime 6, right, which is the bigger rotation. And then it's interesting, right, how the rigid body mode is the same. Okay, for node I, the rotation at both nodes is the same, right? It's the rotation of a straight section. So again, we go and subtract the same quantity, delta prime 5 minus delta prime 2, right, divided by L. Okay, and this guy gets the same interpretation. So this is our total rotation, and you subtract rotation due to the rigid body mode. Okay, and so the remaining item is delta prime 3, right, which is the basic element displacement, and the basic element displacement is as before, right? You take delta prime 4 and you subtract delta prime 1, just like you would do for the truss element. Prime 4 minus delta prime 1. Okay? So again, these are the key relationships that you need to satisfy. Okay? 1, 2, 3. Okay? And so now you see that, okay, on the left-hand side, you get a vector of basic generalized displacements, right? On the right-hand side, you see some functional relationship, right, that's expressed in terms of local displacements. Okay? And so that all that remains to be done is you rewrite it in matrix vector multiplication form. Okay. So let's see. You start with delta prime over bar equals 2. Okay, what you want to get is delta prime 1 over bar prime 2 and delta prime 3 equals 2. Well, you're going to get a matrix, and that matrix will go and multiply the delta primes, right? Prime 1, delta prime 2, delta prime 3, delta prime 4, delta prime 5, and delta prime 6. Okay? And so your remaining task is to basically look at the expressions here and populate the entries of that matrix. Okay? So the first row, right, will have a 1 that multiplies delta prime 3, minus 1 over L that multiplies delta prime 5, and 1 over L that multiplies delta prime 2. Okay? So you put a 0 here, right? You put 1 over L that would multiply delta prime 2, right? Delta prime 3 comes in with multiplier 1. Delta prime 4 doesn't participate, okay? Delta prime 5 gets a minus 1 over L, okay? And delta prime 6 gets a 0. Okay? So this matrix vector multiply exactly represents this relationship here. Okay? Next, you repeat for delta prime 2. Okay? And you see that the entries of the matrix become 0, 1 over L, 0, 0, minus 1 over L, and 1. Okay? Okay? And then the last row exactly represents this relationship here, right? Basic elongation as a result of x displacement, a relative x displacement, right? So delta prime 3, the only guys that will participate is delta prime 1 with a negative 1, 0, 0, delta prime 4 with a positive 1, and this concludes. Okay? And so this equation precisely gives you gamma R BM. Okay? So this is a displacement transformation matrix that sort of strips away rigid body modes. From a vector of element displacements, right, in the local coordinate system. So you've seen this equation before, equals to gamma RBM, right? I've written it many times. Right? It's just for the beam column element, we have an extended definition of this guy, right? That includes rotations, and as a result, that leads to an extended definition of the RBM matrix that is given explicitly by this expression here. Okay. As with everything in structural analysis, right? What happens on the side of displacements, right, must happen on the side of the forces. Okay. So let's look at the force picture. All right, what happens? Well, let's see. So let's draw our element, line it up with a little x-axis here. Okay, we're going to pin it down. We're going to put this guy on the roller. Okay, and let's draw the displacement state, right, corresponds to the basic forces and moments. So you get F over bar prime 3, right, F over bar prime 3, pointing in equal and opposite directions, right? So when F over bar prime 3 is positive, the element's in tension, and if it's negative, it's in compression, right? And then you have two moments. Okay, let's call this guy F over bar prime 1, consistent with our notation, right? And then let's apply this one as F over bar prime 2, okay? And so in this situation, right, what happens is you will get reaction forces, okay, from the application of these moments. So what are those reaction forces? Okay. Well, let's see. If you apply a moment, F prime 2, this way, and the length of the bar is L, okay, then you're going to find, right, that this guy is going to resist that moment, right, and the corresponding force will be F over bar prime 2, right, over L, okay? Vertical force resisting this moment, right? Likewise, okay, if you apply moment F over bar prime here, right, imagine the bar wants to rotate counterclockwise, okay? However, this point here, right, is not going to go ahead and let it rotate. Okay? It will apply an equivalent force, F prime 1 over L, right, to keep the bar in place. Okay? So now, let's think for a second that F over bar prime 1 is 0, okay? So in that case, that force is 0, okay? And it looks like the in the x direction, the element's in equilibrium because F prime 3 point in equal and opposite directions. But in the vertical case, right, vertical forces, it's not, right? Because there is this force F prime 2 that's acting on the element, right, at the leftmost node, and there's no opposing force. Okay? So then what we have, right, in order to achieve equilibrium, there's to be another opposing force here over L, okay, that will counteract this force here. Right? And then the same analysis holds, and then there's another force there, right, which will give you the following force state, F prime 1 over L, okay? And so now everything is in equilibrium, okay? So it's a little bit unintuitive, but just, if you take a moment to think about it, right, because you're applying two moments, right, there'll be vertical forces. And then the force equilibrium tells you that the reaction force at this node has to be this, and the reaction force at this node has to be that, okay? Now, let's go and line this up, right, with the forces in the element local coordinate system. Right, same element, L, right? And in the local coordinate system, remember, we have F prime 1, right, F prime 2, moment F prime 3, and then these repeat, right? F prime 4, F prime 5, and the moment F prime 6, okay? And so all we need to do now is compare the basic picture, right, with a local picture, and just read off the forces. Okay, so what do we get? F prime 1 is the same as minus, right, F over bar prime 3. Okay, I can record this directly. And there shouldn't be an overbar here. So we just rewrite the letter. Right, F prime 1. Okay, next, F prime 2. Okay, well, F prime 2 is the same as this sum here. So F prime 2 equals to F over bar prime 1 plus F over bar prime 2 over L. Okay. Next, F prime 3 equals to, right, exactly the moment that's acting here. Okay. So it's another interesting part, right? Remember, the relationship between the delta prime 3 and delta over bar prime 1, right, involves subtraction of rigid body modes. When it comes to moments, there's nothing to subtract. Okay, that's the whole point. F over bar prime 1. These two are the same. Okay, and then you can go and write out the same quantities for F4, F5, and F6. So F prime 4 becomes F over bar prime 3, right? Just comparing this force here with this force there, right? F prime 5 is that guy pointing down, so you get a negative sign, right? Equals to minus F over bar prime 1 plus F over bar prime 2 divided by L, and then F prime 6 becomes F over bar prime 2. Okay. And just like for the displacements, next step is what? We re-express in matrix vector form. Okay. And in that case, we get something interesting. All right. So now, on the left, I'm going to line up the F primes without the overbar. 1, 2, 3, 4, 5, and then 6. Okay. On the right side, I'm going to have a matrix, which I'm going to fill up one by one, right? This is 6 by 1. And the vector that I want this matrix to multiply is exactly the vector of basic forces, generalized, right? F over bar prime 1, F over bar prime 2, and F over bar prime 3, like this. Okay? So this is 6 by 1, this is 3 by 1. This guy has to be 6 by 3. Okay? All right, and so now let's look at the expressions. Okay? F prime 1 only depends on F over bar prime 3, and that guy comes in with a negative sign. So I get 0 here, minus 1. Okay, F prime 2 depends on the over bar 1 and 2. So I get 1 over L here, 1 over L here, and nothing here. Okay. Then f over bar prime 3 is f1, so I get a 1 here. 0, 0, okay? And then the same holds for the remaining components. I'll just summarize the results. 0, 0, 1 minus 1 over L minus 1 over L, 0, okay? And then I get 0, 1, 0 like this. Okay, and so now take this expression here, right, and compare it with the expression that we derived for gamma RBM, right? And what you find is it's exactly transpose. Okay, which is quite remarkable, but again, not unexpected, right? Remember our discussion about the equivalence of work, okay, in the two coordinate systems. And if you apply a argument like that, you're going to get the same thing. But here, from just the basic force balance, we see that you get gamma RBM transpose, okay? So while gamma RBM relates local displacements to basic displacements, generalized, okay, gamma RBM transpose relates basic forces generalized to local forces. Nothing different, okay, exactly what you saw in the case of a truss, but with the expanded definitions of things, right? So F prime equals gamma RBM transpose times F over bar prime, okay? So as before, but with expanded definitions for F over bar prime, F prime, and as a result, gamma RBM. Okay, and so now formally, right, we actually have the final result. Okay. K, right, which is the element stiffness matrix, in global coordinates equals to, okay, as before, gamma ROT, right, transpose, gamma RBM transpose, okay, times the basic stiffness times gamma RBM times gamma ROT, okay? So nothing here is different in terms of, sort of the notation remains the same, right? It's just that this is new, this is new, this is new, this is new, okay? We have the expanded definitions, right? And the only object that remains to complete, right, is this guy, okay? This is the beam column stiffness in the basic system. Okay. And so for that one, okay, I'll send you back to early lectures. Okay. The very first lectures that we did, okay, where we looked at the problem differential equation and sort of defined the stiffness matrices by basically applying sort of unit boundary conditions to things like displacements and rotations. Okay. So here's our element in the basic system. This guy's pinned. This guy's on a roller. Okay. E, A, Young's modulus, cross-sectional area, right? And we also have moment of inertia, I, right? The length of this guy is L, okay? And again, let me denote by delta 1 over bar prime, F1 over bar prime, right? The corresponding rotation and moment. Here we denote by delta over bar prime 2, F over bar prime 2, the corresponding rotation and moment here, right? And then we had our basic displacement, delta prime 3 over bar, and the corresponding basic force. Okay. So the relationship we need, right, is between the forces, generalized forces, F over bar prime 1, F over bar prime 2, and F over bar prime 3, like this. Okay, 3 by 1. Okay, gonna have a stiffness here. Okay, and the stiffness will multiply our basic displacement vector. Delta over bar prime 1, delta over bar prime 2, and delta over bar prime 3. Okay, so let me separate displacements and rotations. Okay, that imposes the same separation on the matrix itself. Okay, and then recall our developments for the truss. Right, what was the relationship between the basic displacement and basic system that you obtained by solving the corresponding differential equation? It was simple. It was EA over L. Right? Basic stiffness for a truss element. Okay? Now rewind a month and a half. Okay? What was the relationship between the slopes or rotations, right, and the corresponding moments? Okay? What we found is we get 4 EI over L here, right? 2 EI over L here, right? 2 EI over L here, and 4 EI over L there, okay? So the forces are related to axial displacements, right? The moments are related to rotations, okay? And then our model was basically such that we had one independent differential equation for the axial action, right? That gave us a truss, right? We had an independent differential equation in the vertical direction, right? That gave us sort of the Euler-Bernoulli beam, right? And the assumption is that the truss and the beam's bending action are independent of each other, okay? And so what that says is that the entries of the stiffness matrix have to be 0, okay? Meaning elongations generate forces only, right? And rotations generate moments. Elongations don't generate moments, and rotations don't generate forces. Okay, and so this sort of gives us the final piece of the puzzle. Okay. This object here is exactly kappa over bar prime, right? And it's the basic stiffness of the beam column element, okay, that incorporates all of the differential equation and solution to that differential equation information. Okay. Good. All right. So looking at this relationship here, right, you also pick up an intermediate object, which is kappa prime, okay? And this will be the element stiffness in local coordinates. Let's take a look at that. So kappa prime equals 2, right? Gamma RBM transpose, right? kappa gamma RBM. Okay. Right, the rotation matrices will then go and put it in a global coordinate system, right? But for a second, let's stay in the local coordinate system. Okay. And so what does that multiplication look like? Okay, well, you take the gamma RBM transpose that we derived, right? 0, 0, minus 1, 1 over L, 1 over L, 0. Okay. 1, 0, 0, 0, 0, 1, minus 1 over L, minus 1 over L, 0, and then 0, 1, 0. Okay, so you take this 6 by 3, right? Then you go ahead and multiply it by 3 by 3 that we just derived. 4 EI over L, 2 EI over L, 0, 2 EI over L, 4 EI over L, 0, 0, 0, EA over L here. Okay, this is our 3 by 3. Okay, and this guy goes and multiplies the gamma RBM. Okay, let's see if I can fit this here. Need to write a little bit smaller. Okay, 0, 1 over L, 1, 0, minus 1 over L, 0, 0, 1 over L, 0, 0, minus 1 over L, 1, minus 1, 0, 0, 1, 0, 0. Okay, so you can go ahead, right, and carry out that multiplication. Right, so this is 3 by 6, so the end result's going to be 6 by 6. And you get a large sort of 6 by 6 matrix. Okay, that's given as follows. E over L, 0, 0, minus E over L, 0, 0, okay, 0, 12, EI over L cubed, 6, EI over L squared, right? So you're starting to see that the matrix is starting to mix different dimensions, right? 0, minus 12 EI over L cubed, and then 6 EI over L squared, okay? 0, 6 EI over L squared, 4 EI over L, 0, minus 6 EI over L squared, 2 EI over L. Okay. Minus, we need a little bit more room, minus EA over L, 0, 0, EA over L, 0, 0. Okay. An interesting submatrix, right, that emerges. Then you get a 0, minus 12 EI over L cubed, minus 6 EI over L squared, 0, 12 EI over L cubed, minus 6 EI over L squared. And finally, the last row, 0, 6 EI over L squared, 2 EI over L, 0, minus 6 EI over L squared, and here you get 4 EI over L. Okay. There's your 6 by 6 matrix. Okay. If you look closely at the expression, this is exactly as an equation for 20 in the nodes, right? So you can kind of see, you know, by looking at the structure of it, right? If you focus on the first and fourth row and column like this, right? Here you get exactly plus minus EA over L, right? Which would be the kind of a stiffness matrix in the local coordinate system for a truss, right? And then the rest of the entries are sort of coupling, right? So here's your 4 2 EI over L, right? 2 EI over L, 4 EI over L. These are the entries that are sort of coupling the rotational degrees of freedom, right? As you can see, you know, the displacements are not participating, right? But then you have all these other additional entries like this, okay, that sort of couple the displacements and vertical displacements and rotations to take care of rigid body mode. So this, you know, matrix structure is quite complicated, okay. And so finally, right, you can compute K, right, by taking gamma ROT transpose times K prime that we just derived times gamma ROT like this, okay. And here I'm not even going to attempt to write out this expression, okay. I urge you to visit equation 422 in the reader that fully populates that matrix. So you get a full 6 by 6 matrix, okay. And so now it kind of gives you an idea that it's actually easier to do these things on the computer than to do this by hand. Okay, so I think at this stage we know everything we need to know about the beam column element stiffness matrices, and starting from next lecture we're going to do some examples.